Well, good morning everyone. We're looking into the transient transport processes and various examples of that. First category of examples of transient transport processes we have taken is transient heat conduction problem. Now, basically we are looking for the analytical solutions of transient heat conduction problem in the first case, and separation of variable is our tool to solve the problems, the transient heat conduction problem having homogeneous, non-homogeneous or mixed boundary conditions. Now, we have seen that if you have Dirichlet boundary conditions as existing in your boundary, then n pi will be the eigenvalues and sin n pi x will be the eigenfunctions for your solution. Then since you will be having infinite number of eigenvalues, you will be having correspondingly infinite number of eigenfunctions, and when you superpose all these eigenfunctions, you will be constructing the overall solution, which will be having only one constant that has to be evaluated. That constant has to be evaluated from the initial condition that is till unused in your solution scheme, and using that initial condition you will be able to find out what is that the unknown constant in terms of n. So, ultimately you will be getting a series solution. Now, the point comes, suppose you would like to compute some value of temperature or something at a particular location and at a particular time, then how many terms of your series solution you will be taking? It will be turning out that if you take at least first 4 or 5 terms, that will be good enough, because you will be having two parts, one is time dependent and another will be time independent part. In the time dependent part, it will be exponential minus n square pi square value itself is around 10. So, as you go up in higher eigenvalues, it will be e to the power minus 40 times something, minus 60 times something. So, that contribution will be very small. So, overall contribution of higher eigenvalues will be very small towards your solution. So, if you take first 4 or 5 eigenvalues, that will be good enough for your computation. So, you need not to evaluate all the terms in your very high number of eigenvalues in your summation series. If you have Dirichlet boundary conditions, like if your boundary conditions are like at x equal to 0, let us say theta is equal to 0, at x equal to 1, theta equal to 0, you will be getting n pi as the eigenvalues and sin n pi x as the eigenfunctions. Now, we will be considering some more general cases, where these eigenvalues and eigenfunctions will be changed. For example, if you have a Neumann boundary condition, that means a derivative boundary condition existing at x equal to 0, that means at x equal to 0, let us say minus k del theta del x is equal to 0. This means that boundary is insulated. Okay. The boundary at x equal to 0 is insulated. Okay. Now, it heat flux at x equal to 0, the heat flux that is coming in by conduction. So, it will be basically del theta del x equal to 0. It is basically minus k del t del x, and theta is a scaled temperature. Now, in that case, n pi will no longer be eigenvalues will be changed. Correspondingly, the eigenfunctions will be changed. So, the solution that you have already got for these two boundary conditions will no longer valid for this system. Okay. Now, in this class we will just see if let us say how solution will be changed if you have one of the boundaries as Neumann, and if the other boundary is, let us say, mixed boundary condition, again the eigenvalues and eigenfunctions will be changed and the whole solution of the problem will be different. Now, let us consider the first problem. Let us say we would like to solve this problem del t is alpha del square t del x square. First, you understand all these one dimensional transient problem, then later on once these the basic fundamentals of solution schemes are clear to you, then we will go for a higher dimensional transport process like 2 dimensional, 3 dimensional, so on and so forth, and radial coordinates. Now, at t equal to 0, t is equal to t naught, let us say at x equal to 0, it is insulated. So, minus k del t del x is equal to 0, it is basically equivalent to del t del x is equal to 0. So, this is insulated boundary condition. You may be having a non-homogeneous term here like a constant heat flux condition. In that case, minus k del t del x will be is equal to q naught, and you know how to handle those non-homogeneous boundary condition. Anyway, after solving all this, we will be solving a general problem where we will be looking into a complete solution of a general problem. Let us say at x equal to 1, you are maintaining a temperature T is equal to T1, that means a Dirichlet boundary condition is existing here. Now, there are two sources of non-homogeneities at the initial condition and one of the boundaries. So, you make the boundary condition to be homogeneous by doing a origin transfer of temperature. Let us define theta as T minus T1. Okay. With this, your equation becomes del theta del t is alpha del square theta del x square, right. At t equal to 0, transform the boundary condition, initial condition as well. Theta is equal to theta naught, that is nothing but T0 minus T1. At x equal to 0, del theta del x is equal to 0. At x equal to 1, your theta is equal to 0. So, you will be having a non-zero initial condition and homogeneous boundary condition. So, by standard separation of variable, you can proceed to solve this problem. So, we consider the theta is a product of time varying part and space varying part only. Now, substitute this in your governing equation, what you will get is 1 by alpha, after separating the variables, d tau dt is 1 over x d square x dx square. Okay. Again, this is a function of time only, this is a function of space only, they will be equal to some constant. That constant can be 0, positive or negative. If that constant is 0 and positive, you will be getting a trivial solution. So, that does not exist. So, for non-trivial solution, now let us look into the solution of the time varying part minus lambda square, and you will be having a solution of tau as, let us say, some constant Ct exponential minus lambda square alpha t. Okay. This is the time varying part. Now, let us look into the x varying part, d square x dx square plus lambda square x is equal to 0. And the boundary condition, this equation satisfies, are the boundary conditions satisfied by the original problem. Okay. So, the boundary conditions are at x equal to 0, you are having dx equal to 0, at x equal to 1, you are having capital X equal to 0, right. So, the solution of this equation is nothing but C1 sin lambda x plus C2 cosine lambda x. If you do not understand at any point, you please stop me. Okay. So, let us take the derivative of this. This will be C1 lambda cosine lambda x minus C2 lambda sin lambda x. Put the first boundary condition, that is at x equal to 0, dx equal to 0. It means 0 is C1 this will be automatically 0. So, C1 will be equal to 0. So, the solution becomes basically C2 cosine lambda x. Okay. Now, the other condition at x equal to 1, your capital X is equal to 0, it means 0 is C2 cosine lambda. For non-trivial solution, C2 must be not equal to 0. So, cosine lambda has to be equal to 0, and the solution you will be having, there are infinite number of again solutions existing, that is nothing but 2n minus 1 pi by 2, and the index n runs from 1 to infinity. And corresponding nth eigenvalue, your eigenfunction will be C2 cosine lambda n x. So, in this case, when you will be having a gradient boundary condition or a derivative boundary condition, you will be having 2n minus 1 pi by 2 as your eigenvalue, and corresponding eigenfunctions will be the cosine functions. For the case of Dirichlet boundary conditions, you are having sine functions as the eigenfunctions and n pi are the eigenvalues. Now, in this case, the cosine functions are eigenfunctions and 2n minus 1 pi by 2 are the eigenvalue. So, once you get, you can construct the nth solution. Theta n is nothing but product of tau n and x n. This is equal to C1, Ct and C2 will be multiplied and giving rise to a new constant, let us say Cn exponential minus lambda n square alpha t cosine lambda n x, while lambda n is basically nothing but 2n minus 1 pi by 2. Now, the overall solution can be constructed by using principle of linear superposition of all these solutions. So, this becomes Cn exponential minus lambda n square alpha t cosine lambda n x. Index n runs from 1 to infinity. Now, from the initial condition that has not been used till now in the solution scheme, using that you have to evaluate the leftover constant Cn. At t equal to 0, your theta was equal to theta naught. So, put that theta naught becomes Cn cosine lambda n x n equal to 1 to infinity. Now, we have already seen in the last class, I told you to derive those relations that cosine functions and sine functions are always orthogonal to each other. Hopefully, you have already derived that. So, if you do, if you probably take that as granted, now you multiply both sides by cosine lambda m x dx and integrate over the domain 0 to 1. Now, using orthogonal property, if you open up this summation series now, all the terms will vanish apart from n equal to m. So, ultimately you will be getting only one term on the right hand side and one term on the left hand side. So, Cn becomes integral cos square lambda n x. These intermediate derivations we have already done in the last class. Okay. Theta 0, 0 to 1 cosine lambda x dx. Okay. Now, it may happen that your initial condition can be a function of x or it may be constant. If it is a function of x, that functionality will be inserted here and the numerator will be integrated by parts if analytical solution is possible. If not, a numerical solution using trapezoidal rule or Simpson's rule should be employed. So, the integration of this thing will be half, right. It will be 2 theta 0 cosine lambda n x. So, it will be integration is sin lambda n x divided by lambda n from 0 to 1. This becomes 2 theta 0 by lambda n sin lambda n sin 0 0. So, this will be the value of Cn. Okay. So, theta 0 your theta is summation Cn is 2 theta 0 sin lambda n over lambda n exponential minus lambda n square alpha t cosine lambda n x, and theta is nothing but t minus t1, right. So, t as a function of x and t will be equal to t1 plus to 1 to infinity 2 theta 0 and then square alpha t cosine lambda x. Okay. So, this constructs the complete solution, and again as we have discussed earlier, for computing some values only 4-5 eigenvalues 4-5 terms of this summation will be good enough, because the higher order terms will not contribute much towards the complete solution. Now again the eigenvalues and eigenfunctions will be changed if you have one mixed boundary condition. That will be, let's say that boundary is open to atmosphere. So whatever the heat is conducted at that boundary will be convected away by the forced convection that will be imposed by external environment. So it will be system something like this. This is, let's say, at x equal to 0 and this is equal to x equal to 1, and this boundary you are maintaining, let's say, at a temperature T1, and this boundary is open to atmosphere. That means whatever the heat that is coming here will be convected away by the external turbulence. Let's say T at ambient is T infinity. So it's a mixed boundary condition. So that is the amount of heat that is conducted at this place will be minus k del T del x, that will be at x equal to 1 should be equal to h T minus T infinity if at any point of time T infinity temperature is lower than the temperature of this body. Otherwise it will be flowing in the opposite direction. Okay. So what is the now our interest is to find out temperature within the body at any point x at any time t. The governing equation remains the same. Del t is alpha del square t del x square, and at t equal to 0 the initial condition is at t equal to 0 you are having, let's say, t was equal to t naught. The boundary conditions are at x equal to 0 you are having t is equal to t1, and at x equal to 1 you are having k del t del x plus h t minus t infinity is equal to 0, right. Now if you make this equation to be non-dimensional, now let us look into the various the non-homogeneities, etc. The initial condition is non-homogeneous, this boundary condition is non-homogeneous, this boundary condition is also non-homogeneous because of the presence of the term h times t infinity, right. H times t infinity makes this boundary condition non-homogeneous. So again you can scale or define your temperature as, let's say, theta is equal to t minus t infinity. If you do so, then this boundary condition becomes homogeneous. Let us define theta as t minus t infinity. In that case your governing equation becomes del t del theta is alpha del square del theta del t is alpha del square theta del x square, right. At x equal to t equal to 0 your theta was equal to theta naught, that is T0 minus T1 T infinity, right. At x equal to 0 your t was t1. So, your theta is t1 minus t infinity, let us say theta 1. Okay. Now, at x equal to 1, your k del theta del x plus h theta is equal to 0, right. Again, you will be having 3 sources of non-homogeneity. Now, let us we will solve this problem later on. Let us slightly modify for the ease of solution. Let us slightly modify the boundary condition. Let us say that this boundary condition is open to atmosphere, that is fine. Let us maintain this boundary at the same as ambient boundary, ambient temperature. Okay, let us just change the problem slightly. Let us say we are maintaining the temperature at the boundary x equal to 0 as the ambient temperature. Okay, let us say t is equal to t infinity here. Although this is a more general problem and we will be tackling this problem later on. So, t is equal to t infinity here. So, in that case this boundary condition becomes homogeneous. Okay. Now, you will be having a linear partial differential parabolic equation, non-zero initial condition, homogeneous boundary condition, and this is also homogeneous. So, you can go ahead with the standard eigenvalue separation of variable. Again, that means your solution is constructed of 2 products, one is time dependent, another is space dependent. Okay. And you insert this equation into the into governing equation, and after separating the variables, this becomes alpha tau d tau dt is d square x dx square 1 by x, and this constant will be a negative constant. Okay. Now, the time dependent part remains the same. Now, here you will be having a linear partial parabolic equation and non-zero initial condition and homogeneous boundary conditions. Okay. So, the standard separation of variable can be used unless and until, you should remember this, unless and until either by doing some simplification, by some kind of transformation, or by some mathematical treatment, unless and until the boundary conditions are not homogeneous, you should not use separation of variable. Starting a problem, you should look into that, and once the problem is cast in this fashion that your equation is linear, non-zero initial condition and 0 boundary conditions, that means homogeneous boundary condition, then only you have to apply separation of variable. So, the time varying part becomes minus alpha lambda square t. Now, let us look into the spatial variation. It is d square x dx square plus lambda square x is equal to 0. Okay. Subject to the x part, the spatial part must be satisfying the boundary conditions of the original problem in the space. That means, at x equal to 0, your capital X is equal to 0, at x equal to 1, you had k dx plus h theta is equal to hx is equal to 0. That means, dx plus beta x is equal to 0, where beta is a constant and it is h by k. Okay. Now, in a problem, suppose we have considered the x dimension in dimensional space, that is from x varies from 0 to 1. In a typical problem, x is varying from 0 to some finite thickness L. So, in that case your x star is defined as x by L. If you do that transformation, then only this x is scaled down to 0 to 1. So, in that case this boundary condition in the non-dimensional form in 0 to 1 scale, this becomes HL by K. Okay. In an actual problem, I have taken it for simplicity, x is already 0 to 1, but for an actual problem it will be from 0 to L. In that case, to make x to be in a range 0 to 1, you have to define x star as x by L, and in that case the non-dimensional, let us say dx star plus hx, this becomes HL by K, right. And what is HL by K? This is a Biot number. Biot number, it is a ratio of resistance for the convection towards the and the resistance of conductance. Now for Biot number less than 0.1, you should forget about all this analysis, because there is a lumped system analysis. In that case, no spatial variation is recorded, that is not significant. If that is not so, then this analysis has to be carried out. So remember, this is a beta, a constant here, but in actual case this beta will be identified as Biot number, which will be constant for a particular system, because for a particular system H you can estimate from a different correlation. Convection correlations are available that we will study in the next semester, from where you can calculate, you can estimate H, the heat transfer coefficient, K, thermal conductivity of the solid, that is known to you from the, it is a property, and L is also known. So you can calculate what is the Biot number, and it is a constant unless and until this H and K are temperature independent. Okay, so the solution of space varying part is C1 sin lambda x plus C2 cosine lambda x. Now at x equal to 0, your capital X becomes 0, that means 0 is C2 is equal to 0, that means x equal to C1 sin lambda x. Okay. Now at x equal to 1, your dx plus beta x is equal to 0, that means dx is C1 lambda cosine lambda x plus beta C1 sin lambda x. The whole thing will be evaluated at the boundary x equal to 1, and then it will be equal to 0, right. So C1 lambda cosine lambda plus beta sin lambda equal to 0. Now in order to get a non-trivial solution, C1 should not be equal to 0, that means beta tan lambda plus lambda is equal to 0. Now instead of getting an explicit expression of lambda like the previous two cases, in one case we had a lambda n is equal, lambda is n pi, and in another case it is 2n minus 1 pi by 2. Now here you have to solve a transcendental equation, lambda is equal to minus beta tan lambda. Now if you solve this transcendental equation, you will see that it will, suppose f lambda is lambda plus beta tan lambda, then f versus lambda, it will cut infinite number of points. So infinite number of roots existing for this system as well. So for every root, so this is a transcendental equation for lambda which has infinite roots. Right, and those will be corresponding to 1, 2, 3 like that. So lambda n is the, let us say, nth root, and n equal to 0. So lambda n is the eigenvalue, nth eigenvalue, which is basically the root of this equation. Now you can use Newton-Raphson algorithm or any search algorithm to get the root of this equation numerically. Okay. Now interestingly, in fact, in numerical recipe, there are lots of there is a book called Numerical Recipe in Fortran as well as the corresponding book in C language. Okay. Now in that book there is a CD comes which contains all the subroutines. Those are written in that book, discussed in that book. Okay. So you can use any numerical recipe subroutine as well for using Newton-Raphson. So you need not to write your own code. You can write your own code as well. Now for a given beta, this the n number of solutions will be, you will be getting all the solutions. Now if you use your own code, I can tell you that this equation will be having roots in the difference of roughly 3. If the first root is 1, then next root will be 4, the next root will be around 7, next root will be around 10, next root will be around 13, so on so forth. Okay. Suppose you are using Newton-Raphson, probably almost all of you have used Newton-Raphson at some point of time. Okay. So you start with now the basic problem with Newton-Raphson is the solution, you will be getting the solution root which is the closest to the guess point. Now since there are infinite number of roots, so it will be basically you have to search blindly where you are at what point you will be giving the guess value. Suppose you give the guess value around 6, it will be converging to 7. Suppose you give a guess value, let us say 4.5, it will be converging to that point 4. Now it will be overlooking all the other roots. Okay. So what you have to do, so you give a guess value, let us say 0.7 or 0.5 or 0.8. Okay, it will converge to the first root. It may not be 1, it may be 1.4, something like that. I am just giving you some example. Okay, I do not remember all the values of the roots. Now it will be converging to that root. Then put a do loop on the guess itself. Okay, you carry out a Newton-Raphson in a loop by giving an increment of the guess value by 3. Okay. So when the first loop starts, it will converge the value at the first root, let us say 1. Then in the next case, let us say you are given a guess, let us say around 0.7. So you give 3. So in the next loop, when the next loop starts, the guess value starts at 3.7. So that it will be converged at 4. Okay. In the third loop, the guess value will be 6.7. Okay, it will be converging the third root 7. Suppose you would like to have 10 roots or 5 roots, you put a loop, you assign any I equal to 1 to 5 to the external loop. So you will be getting first 5 eigenvalues. Okay. And xn is the corresponding eigenfunction and it will be again sine function. Okay. So lambda n are the eigenvalues and xn's are the eigenfunctions. The whole solution again can be constructed by theta n is tau n multiplied by xn, a new constant Cn exponential minus lambda n square alpha t sin lambda n x. Now the whole solution can be constructed by, the overall solution can be constructed by superposing all the solution n equal to 1 to infinity is summation Cn exponential minus lambda n square alpha t sin lambda n x. Okay. Now what is left is the evaluation of this constant Cn which will be obtained from the initial condition. Theta 0 1 to infinity Cn sin lambda n x. Okay. So using the the sine functions are orthogonal to each other. So using the definition, you can evaluate zero to 1 x dx, right. Now you can now the solution will be a little bit different. Just try to evaluate the numerator as well as the denominator. You will see the difference. Now if you evaluate the numerator, zero to 1 sine lambda n x dx, and it will be cosine lambda n x, right, minus cosine lambda n x by lambda n 0 to 1. No, I am just evaluating the numerator. Yes, there will be a theta naught here. That is fine. So it will be 1 by lambda n, 1 minus cosine lambda n. Okay. Now let us look in the denominator. Zero to 1 sine square lambda n x dx. Okay. This will be twice sine square lambda n x dx. Now cosine 2x is 1 minus 2 sine square x, right. So 2 sine square lambda n x basically 1 plus cosine 2 lambda n x. Right, 1 minus cosine 2x. Yes. Right. The first term will be 1. The second term will be sine 2 lambda n x divided by twice lambda n 0 to 1. These will be 0 to 1. This is already evaluated. Okay. This becomes half 1 minus 1 by 2 lambda n sine 2 lambda n minus sine 0, 0. Okay. Now sine 2 lambda n is nothing but 2 tan lambda n divided by 1 plus tan square lambda n, right. And what is your eigenvalue? Eigenvalue is the root of lambda n plus beta tan lambda n is equal to 0. So you can substitute tan lambda n in terms of lambda n and beta. So you can slightly simplify this equation as well. So you need not to deal with any more trigonometric functions. So 1 minus lambda n, tan lambda n is nothing but minus lambda n by beta. One plus lambda n square by beta. Okay. So it becomes 1 minus plus this lambda n will be cancelled off. This beta square will go up. There will be a beta in the numerator only. Beta square plus lambda n square. Right. So we will be having half lambda n square plus beta square, lambda n square plus beta square. Okay. So this will be the the fate of the simplified form of the denominator, and let us look into the Cn. The Cn becomes theta 0. The numerator was 1 over lambda n, 1 minus cosine lambda n, and the denominator becomes this half will be 2 lambda n square plus beta square divided by lambda n square plus beta square plus beta. Okay. So, that will be the solution for Cn. Now you can get the complete solution, that is theta is nothing but t minus t0, right, t1, that was Cn exponential minus lambda n square alpha t sin lambda n x. Where lambda n are the roots of that equation and Cn will be this. So, again you take the first 5 eigenvalues, evaluate this summation series and get the profile of t as a function of x for a particular time, or for a particular location get t as a function of x, or for a particular x and t combination you will be getting a local value. Now, again one more trick that you should remember, that suppose if you remember that in all the cases at x equal to 0 we have started with a Differential boundary condition, theta is equal to 0. For the case of Neumann boundary condition we had del theta del x is equal to 0, and for the case of mixed boundary condition you had a Differential boundary condition at x equal to 0 and at x equal to 1 you had a mixed boundary condition. Suppose your system is something like this. Let us say this is at x equal to 0, this is at x equal to 1. You are maintaining a temperature T is equal to T infinity here. This boundary is open to atmosphere. You are having a mixed boundary condition at this boundary. Now, again you are asked to find out what will be the temperature as a function of x and t within the body. Now, if you start with the problem, because your governing equation remains the same, del t will be is equal to alpha del square t del x square, and your let us say initial condition is t is equal to 0, t is equal to t naught. At x equal to 0, at x equal to 0 you will be having the mixed boundary condition. So, k del t del x plus h t minus t infinity is equal to 0, and at x equal to 1 you are having t is equal to t1. Now, if you can let us say this is t infinity. Okay. Now, you can define a temperature theta is equal to t minus t infinity. By doing so, you can force this boundary condition to be homogeneous, and again this will be non-zero initial condition. But there will be a problem here. Now, if you start the problem something like this, then let us see what the problem will be facing. So, ultimately your equation will be del theta del t is alpha del square theta del x square. At time t equal to 0, your theta is theta 0. At any t at x equal to 0, your theta was it is basically mixed condition. So, del theta del x plus beta theta is equal to 0, and at x equal to 1 you are having theta equal to 0. Okay. Now, if you start with this, then you will be facing a problem to evaluate the eigenvalues and eigenfunctions. Okay. Now, let us look into the problem. Let us see what we can face. The spatial part. Let us look into the spatial part capital X. Okay, the governing equation will be d square x dx square plus lambda square x is equal to 0, subject to at x equal to 0 dx plus beta x is equal to 0, at x equal to 1 your capital X is equal to 0. Okay. So, the solution is nothing but C1 sin lambda x plus C2 cosine lambda x. Okay. Now, what is dx is C1 lambda cosine lambda x minus C2 lambda sin lambda x. Now, let us put the first boundary condition at x equal to 0 dx plus beta x is equal to 0. At x equal to 0, what is dx? It is C1 lambda cosine lambda x. Cos 0 is 1, C1 lambda. Okay. And what is x? X is C2, right? X is C2. So, dx plus beta x. So, C1 lambda plus beta C2 is equal to 0. That is the relationship between C1 and C2 you will be getting from the first condition. Now, let us look into the second condition. At x equal to 1, your 0. That means 0 is C1 sin lambda plus C2 cos lambda. Okay. And C1 is minus beta C2 by lambda, minus beta C2 by lambda sin lambda plus C2 cosine lambda. So, take C2 common, it will be cosine lambda minus beta sin lambda by lambda. Okay. So, for a non-trivial solution, let us say you will be having again tan lambda, this is lambda by beta, a transcendental equation. The roots of the, again there will be infinite number of roots of these equations, and all the roots will be corresponding to the eigenvalues, individual eigenvalues. Now, let us look into the what will be the fate of eigenfunction. The eigenfunction becomes, I mean, in this case both C1 and C2 are not equal to 0. So, it will be C1 sin lambda n x plus C2 cosine lambda n x, and C1 and C2 are related by C1 is minus beta C2 by lambda sin lambda n x plus C2 cosine lambda n x. Okay. So, C2 will be in common, cosine lambda n x minus beta by lambda sin lambda n x. Now, this eigenfunction does not fall in the standard category of the eigenfunctions, those are the sine and cosine functions. And when you would like to evaluate the final constant in your equation, you cannot use the orthogonal property of the sine and cosine functions, because it is a mixed type of eigenfunction. So, there may be some ways to handle this, but the easiest way to find out to solve this problem is you change the coordinate of the system. That means, what was the original problem? Original problem was del theta, del t is alpha del square theta del x square, t is equal to 0, your theta was equal to theta naught. At x equal to 0, you had del theta del x plus beta theta equal to 0. At x equal to 1, your theta was equal to 0. You change the definition of x. Okay. You define x star, let us say y 1 minus x. Okay. Now, what is del theta del x? When theta is equal to 0 at x equal to 0, then you will be getting sine functions of the eigenfunctions, and you know all the algebra, the leftover algebras are very simple. When you have a Neumann boundary condition, you will be having the cosine functions as the eigenfunctions, and using the orthogonal property of sine and cosine functions, you can simplify the algebra, the leftover algebra. So, in order to get that advantage, to take that advantage, you define your coordinate y as 1 minus x. Now, let us see what is del theta del x. Del theta del x is del theta del y del x, right, and y is 1 minus x. So, it will be minus del theta del y. So, it is del square theta del x square, it will be del x or minus del theta del y. So, it will be del y of minus del theta del y del x. So, del y del x is minus 1, this minus 1 is already there. So, it will becomes del square theta del y square. Okay. So, your governing equation remains unchanged, del theta del t is del square theta del y square. At t equal to 0, theta remains as theta naught. Now, the boundary condition at x equal to 0 will becomes the boundary condition at y equal to 1, because of this definition. X equal to 0 means y equal to 1 and x equal to 1 means y equal to 0. That means, at y equal to 0, we are having theta equal to 0. At y equal to 1, we are having the other one, del theta del y with a negative sign minus beta theta. Okay. Now, this is what is this is a standard eigenvalue problem again, and putting this Dirichlet boundary condition at x equal to 0, you will be getting eigenfunctions as sine functions. Yes, just one sec. So, you will be getting the standard eigenfunctions, and this lambda n will be the roots of the transcendental equation. And the rest algebra remains same. Okay. Remains same, and you will be having finally t as a function of y and t. And now you replace y as your original coordinate, y as a function, y as 1 minus x. Okay. So, you will be finally getting t as a function of x and t. So, whenever you will be using separation of variables, so be a bit careful. That means your initial condition has to be non-zero, your boundary conditions have to be homogeneous. The first boundary, the boundary at x equal to 0 should be a constant boundary condition or a derivative boundary condition only. Otherwise, you have to do some kind of tricks, some mathematical tricks to bring that in the same format. Okay. We will continue again some of the complicated problem in the next class. Thank you.
So, we were studying fluid mechanics up until this point, but now we are going to go into a similar process called heat transfer, the basics of which we have introduced in previous classes. We all know we are going to restrict ourselves in the first part of this course to conduction transfer process, conduction heat transfer. In what we have seen is the major equation which defines the thermophysical property, thermal conductivity, is Fourier's first law of conduction. There we have seen is that the heat flux is proportional to the temperature gradient, and the proportionality constant is K, the thermal conductivity, and we have also seen that Q should be equal to minus K dt dx or Q double prime. The minus sign signifies that the heat travels from high temperature to low temperature. One of the major objectives of conduction heat transfer is to find out the temperature distribution in a solid as a result of the changes that are taking place in its boundaries. Apart from that, there may be a situation in which heat may be generated inside the system as well, the combined result of which is a change in temperature, maybe with time, maybe with position inside the solid object. What we will try to develop today is some equation which would give us the temperature inside the solid as a function of its position as well as its function of time. So, but then again we are not going to deal with transient heat transfer. In my part of the course, transient processes will be handled by Professor Dev. So, I will restrict myself to steady state heat transfer in different geometries utilizing the heat diffusion equation. Now, in order to develop the heat diffusion equation, what we are going to do is, again we are not going to go for all the steps, rather we will only highlight the important steps. That is why it is more akin to that of a diffusion process, where the transport is by molecular mechanism. So, that is why this is known as heat diffusion equation. Okay. So, this is the most general form of conductive heat transfer inside a solid object, and similar to this one, which is in Cartesian coordinate, I can also have the same expression for cylindrical coordinates and for spherical coordinates, which are given in your text. I am not going to go into the derivation of that. So, transformation of coordinates would give rise to slightly different form of this equation, but the basic concept would still remain the same, that it is going to be in minus out plus generation is equal to the rate of energy storage or rate of change of energy storage in the system. All right. So, we can see several simplifications possible of this equation. The first one is, I can take K outside and it would simply be times K times del 2 T del x square plus del 2 T del y square plus z . I can make this one. So, what are the assumptions that I have made in this? K independent of x, y, z, that means its position.